Today I'm going to talk about this two-dimensional nanosheets for flexible and stretchable electronics, how it going to be used, and what are the techniques I was using to do this material for stretchable applications. So here I'm just going to give a small overview about this technique I'm doing, and the work in the future also I'm going to discuss what are the things we can do later further to enhance the property or improve the stretchability like that. Today I'm going to focus on the particularly about the energy and how the principal talked about energy. So here also in if in future flexible device can come into the real life application, at the time the flexible energy device also necessary. So it is very important to develop the stretchable energy devices also. So I was doing one work in that aspect. So I'm going to concentrate about that one. I'm not going to discuss about the transistor and sensors about that. I'm just going to discuss about the energy related supercapacitors. And to this is my content today. I'm going to just give the overview about the what is electronics and what is stretchable electronics and what are the techniques can be used to develop this stretchable devices. And then I'm going to discuss about the my work, how the supercapacitors in stretchable case we can prepare or fabricate and measure the devices. So I'm going to discuss about all those things. Um, for for the students, this is what is electronics. Everybody knows it. It is electronics is a simple things. It's nothing but the movement of electrons. Once the movement of electrons is in a semiconductor, for example, it's from the just from the valency band to conduction band or intra band or one atom to another atoms. So is generally just basically is simple as that. The movement of electron is called the electronics. So in that electronics, it was we have a long history of the electronics, and we until now we have this solid state related electronics on our hand. And this electronics is basically three types. One is like solid state. Currently we are having the our mobile phone and computers or laptops, everything is comes under that one. And the components are developed like from capacitor to transistor, everything is made of solid material. So the materials are the devices with deals with a solid substrate and solid components, that is called solid state electronics. So that is the current existing commercialized electronics we are using it. And now slowly the flexible electronics is coming into the picture. And for example here we you can see that the flexible electronics, the basic rule, it should be bendable, inward or outward bending, it doesn't matter, it should be bendable, and it should be rollable or foldable. So now the foldable LG or Samsung, they already established the this is actually Samsung LG in 2013. They already devised this one, and now it is commercialized. Actually, they have developed like flexible real flexible device and foldable device. Particularly foldable device is already commercialized. And the basic building blocks of this is the inorganic brittle material. They can be molded on top of the flexible substrate. For example, it is like PET or polyimide, like that PI substrate. These are the two major substrate people use. And then the PCB boards, printed circuit boards also, they made with that PI or the thin glasses. So those things can be bendable outward or inward without it's the bending ratio will be very less, but it can be bendable. So if you evenly you're fortunate and unfortunate, your phone might be fall down. If it is in the flexible state, due to this bending ratio, they can be sustained even if fall down on the floor. So so that is the advantage of this flexible electronics. And future, very soon, I think within a 5 years time, we will have a real flexible smartphone in our hand. I'm hoping that. The next is the stretchable electronics. This is the future electronics. Actually, it is like based on basically like the generally in our country, the ladies use the rubber band, right? It is like when you stretch it and use it, and then if you release, you take out from your hair, the band goes to its original position. It's same thing in stretchable electronics. The devices, all the devices is like it will be like stretching, then it comes to its original. When you release that stress, you give the strain or stress you given, if you release that one, it will comes to original place. Here I shown that they are this biaxially stretchable device, and they are blown some led over with that one. I think this is a transistor array. And the basic condition for stretchable is it should be, the device should be elongated or twisted like this. So these are the two real thing is needed for the stretchable electronic device. And the minimum stretchability of the material should be 2.3. So be less than 2.3% stretchability, the material will not be useful for any stretchable application. So you need at least 2.3% of stretchability, because your skin, the minimum stretchable of your skin will be 2.3. So it can stretch maximum like 10 15 also. If we are getting old, then the skin can stretch larger, but you need a minimum 2.3%. If you are taking some inorganic material, it has for example, if it is you are taking as a gold thin film or something, if it has a 2.3, more than 2.3 percentage of stretchability, then you can use that material into the stretchable electronics. And it also based on it's also depends upon the thickness. So if you have a thick layer, it will crack very easily. So if you go by thin layer like nanometer, few nanometer, then you can extend your stretchable ratio percentage also. So that is the basic difference between these solid state, flexible, and stretchable electronics. Is the major thing is in flexible and solid state, the components are made of inorganic material, and the substrate only changes the substrate. The PCB board is the difference. But in case of stretchable electronics, the whole device has to be stretchable. So this is like 100 times difficult than the flexible electronics. So it is, but it will be very useful in many aspects. So next slide, I'm going to talk about this is the growth. Actually, this is the history of our electronics. And see the distance between our electronics instruments and us, it is keep on reducing when the year goes along. Because when the radio was there in the corner of the room, now the TV also, it is in the corner of the room. Then slowly, if laptop, then it is comes to our lap. So it is the distance was increasing between the human and the machine. Distance was keep reducing when the electronic device evaluation takes place. And finally we will have the mobile phone in our hand. So then it is comes to like a millimeter to centimeter distance from our hand and the phone. So now the future stretchable electronics is implantable electronics. So it can be implanted into your skin or your device. So the distance is really nullified, and it is zero. So that is why the growth will make it. So that when you make the successful device in stretchable, then there are so many particularly medical applications are very huge, and there is a lot of potential for that application in the future. So that's why like this implantable or attachable, it is actually attached in the cloth, our dresses. When we have that one in, it can be transmitted, the sensor, it will be attached with the sensor, it can be transmit your observed signal like blood pressure, or even sugar can be tested these days, and some people reports are coming on that. And it can be so those kind of things, and will be tested very easily. If you have a baby, very young baby, like 6 months 7 months old, it you are it is having the fever or not, we without just with the patch, so stretchable patch, thermal sensor, with that one, if you attach in the back of our the neck, you attach, and the baby can sleep it. At the night time, if it is some fever, then automatically it will, the temperature rises, and then immediately they sense, the sensor sense the temperature rise, and it will give the signal to your mobile phone, ringing or alarms, so you can check and check about the baby. So these kind of very real life application going to come in the future. But it takes a little longer time, because it's a little harder, like 100 times harder than the flexible electronics. So why stretching is good? Always it is like the stretchable means, why we have already flexible and solid state electronics. We are almost comfortable in life. Why we need stretchable electronics? That question might arise all students' minds when we see this. Why another technology? What is the necessity? So if we think like that, here are the answer for those questions. And if for simply, if you stretch your body, you feel some, if your muscle crack or anything, something, you will have some pain. If you give some massage or some stretch, you will suddenly the pain, you can feel that you feel relaxed. So stretching to the body itself, feeling good means, it is like doing exercise will give you like your blood pressure, everything will be normal, and blood flow will be good, and at the time you, the muscle cramps or something will be really, you feel better. Similarly, if you have a stretchable electronic device that can work like your body skin or your part of your body, then it will be easily, you can directly detect that problems, and then you can use it, like whatever the signal, like if for example here, this is the electrocardiogram, and it is like with you can attach to your body, as well as you can attach to your dresses, and it will automatically sense if it is, without stretchable, it will break down. If while washing, it will be break down, or if you bend, or it will be broke down. So if it is stretchable, then it will be like always you can utilize this. It is durable for longer time. So this is one of the application it's coming up, and in Korea, some of the place already they are selling these kind of products. And this is the like cardiac mapping. This is the stretchable electrode based sensor. It was attached to the heart. Then it can be also sense your heart is working better, or if any problem, it can we can stimulate your heart. So this kind of application is possible in the near future. So that's why we need for the biomedical application, where the stretchable electronics going to help more. So next one, the common basic things. And if you, now your phone, if it is falling from your hand, you will say ayo, like that, some expression we will give, we will shout, and so we will get angry. It will not work once it fall down, because of this problem. It will crack, the display will go down, or it will be broke down. So due to this problems, our phone, we are always, so many people in a year always changing their phone because of these problems. So we cannot live this modern world, we cannot live without the smartphone, so we need it. So in order to improve this kind of things, if your device is made of stretchable material, then if it is falling down also, it won't break down like these things. So think about it. If it is the stretchable, your phone can be rolled like elastomer like this, and you can put it in your pocket. Now if you are wherever you go, you put it your phone in the front pocket and you sit. Okay, if you have a stretchable electronic device, you even in your back pocket, you can put it in your back pocket and you can sit it. It will nothing will happen. So the another aspect of this stretchable electronics, it's have a huge potential in the coming year for the business. Actually, if someone want to invest, this is one of the area. If new entrepreneurs were there, they have enough money, then they can be invest in this field, because this is the one company, they have markets, they used to calculate in, and it will they identified it that in 2023 it will be 411.85 million US dollar market will be there for this stretchable electronics alone. Then it will be rise, year goes on, it will definitely, it will be going up. So there is a huge potential business opportunities, as well as there is a research opportunities to improve our life further. And the third, this is the first two are the real important stretchable electronics, and this is another aspect. This is also can be possible, like human machine interfacing or soft banking, this soft robotics. Now we have robots with metals and soft robotics, then it will have a different the feeling sensing applications are really possible when the stretchable electronic comes. The robot can have a sensitivity like human. It's the robot, the Endran movie talks about the similar things will come when we stretchable electronics will be developed further. And for this stretchable electronics, the fabrications are quite tricky. There are few approaches available. I'm going to talk about, there are three major fabrication approach available for this, excuse me, approach available for this fabrication process. And they are first approach is the silicon island approach. Means that if you have because why this approach is the initially they developed this approach because already the electronics are made with silicon, so they started with that one. The Professor Rogers from Illinois the State University, they are the really pioneer of this kind of researches. And they have initially we will have a small thin layer of silicon wafer, and they cut it like with the proper etching technique and lithography. They make it like solid pattern with the transistors, and they connect. This is the electrode actually. Like they make that electrode stretch, and then they use this as a stretchable electrode. And then stretchable device. And here is the simple version of this whole setup, whole thing. And you can see that this part is the non-stretchable solid device part. Like here we can mold the transistor, sensor, anything. And this is the stretchable. This structure is called serpentine structure, and it will have that arcs leg we will put, right? That I forgot that name. So we like that structure. It when you stretch it, this whole setup will be mounted on the flexible or stretchable substrate. And if you stretch it, only this electrode part will stretch, and this main device part will not get affected. So it is one way of engineering approach to get the work done. Like means like you will fabricate a stretchable device, but it is not, the material is not really stretchable, it is inorganic. but only the approach, with the approach the electrode is stretching. So this will be useful for the one kind of application. This approach is really useful, and it this approach is also gives the high performance, because when the next part I will discuss, when go to the organic material, their efficiency was really poor, because the silicon is we are using, because its efficiency was very good. So that's why we already have the solid state commercial electronics. So this the same material can be utilized to stretchable electronics in this such a way. This approach is called island approach. This is each one is island here. This they mean this is island, and then the island is not stretchable, and the electrode only stretchable. This electrode, this is serpentine electrode, and this is the first approach they develop. And then the second approach is like here the substrate, the PDMS means polydimethyl siloxane. It is one of the polymer with based on silicon compound, and it will like it is elastomer. It will stretch like our rubber band, and if you initially you stretch it in one direction, uniaxial stretching, then you mount your whatever the material you want, silicon, gold, whatever you want, then you release it. When you release, you will make this kind of bubble buckling structure. This buckling structure will be when you release, it will form this structure. So it will be there when make the device with this released state, and then you stretch it, then it will be stretchable, as work as a stretchable. And this is the real cross-sectional view of this setup. And here the elastomer structure, and this is the inorganic material, whatever it is, gold or any aluminum oxide or whatever it is, you make it like with this pre-stretching position, then release it, you make this buckle structure. This will help to make your device stretchable. And if you want to make the same thing in, this is actually uniaxial. When you want to make it in biaxial, means both sides structure, then you have to initial stretching will be in two sides. You have to stretch it like X and Y, and then you transfer your material, then attach it, then release it. So your whole device will be stretchable, both biaxial is stretchable. So this is the second approach people use, because here also the inorganic material can be used. It will give the better efficiency than the organic compounds. And the third approach, this is the real approach. It was the one of the best approach, because here it is always use the intrinsic material. When we use the inorganic material, those are non-stretchable. When intrinsic means it has to with the ability of stretching from its own. நம்ம தமிழ்ல வந்து சுயம்புன்னு சொல்லுவோம் இல்லைங்களா, அந்த மாதிரி ஒரு சுயம்பு அவனே வந்து தானா வந்து முளைச்சு வர்ற மாதிரி, ஒரு போராடி வர்ற மாதிரி அவன்கிட்டயே உள்ளார ஒரு இருக்கக்கூடிய ஒரு ப்ராப்பர்ட்டி. ஸோ த இன்ட்ரின்சிக் ப்ராப்பர்ட்டி, when the intrinsic property comes to the material, if it is stretchable is the intrinsic, then it is really good for this application. So people develop these kind of things. It will be the real good for the stretchable electronics development. This approach is based on the polymer semiconductors or polymer or organic polymer composites. They use this material like this polymer. They always choose like it has this crystalline part as well as amorphous part. Then it is kind of island like structure, but this as the polymers are already, if you take polymer, they are semi-stretchable, so they are not fully stretchable, semi-stretchable. Here this polymer has the advantage like structure. There is amorphous region and crystalline region. When you stretch it, the amorphous region will be stretched. The crystalline region they won't stretch it, but when the amorphous regions stretch and they break down due to the hydrogen bonding breakdown, they breaking, then when you release, the hydrogen bond is very easily can bond to form again, and that's why the stretching cycle will be possible with this one. From in the Stanford University, Professor Somaya, she's Somaya Bavo, they use like this material approach. They are one leading group. They developed already human machine interface like electronic skin devices. So they are the one using this approaches here. Then the intrinsic stretchable unit device. This is the same thing. It is like means that all the material should be intrinsic, like substrate, electrode, semiconductor, or insulator, whatever the component you are using for a single device, their all should be intrinsic. Intrinsic, then the real stretchability will come into play, the development of the stretchable when if it is really intrinsic, then the recovery, like after release, it goes to the original position. So when if it is inorganic or this previous island structure or the buckling structure, they are the original position after relaxing, the original position is will not come to real to zero. But with this technique, particularly with intrinsic approach, it will come to original position. If you are starting from zero, it will come to zero. So that is the real advantage of this approach. So this is the major three approaches people use to fabricate this stretchable electronics devices. And now I'm going to introduce this nano sheets. Until now, only people used metallic sheets like gold sheets or copper sheets and silver sheets, and these are the sheets people used for stretchable electronics, and they used with a different approach. So here my work is my aim is to utilize this nano sheets for stretchable electronics. Why? Because this nano sheets contain like all the components which electronics is needed. Metallic is there, insulator is there, semiconductor is there. So even sometimes you can use the insulator as a substrate. So this as the nano sheet, it is open up now. More than 50 type of nano sheets are available. So it can be like so it is variety of applications are possible. Now here people used copper, gold, silver as a stretchable electrode material. Nobody used as an active layer for any stretchable like active layer means as a semiconducting material or as a energy storage material. So I'm going to my aim is to develop those things like stretchable semiconductor and stretchable energy storage device. These kind of things I'm going to develop. That is my aim. So that is focus of my work. And actually I was developed all these things like metallic phased here 1T MOS2 means metallic phased MOS2. I will discuss in the later part, and it will have this application of energy storage and actuator. So and then this is insulator boron nitride, and they have a insulating property and thermoelectric property. They under stretching condition I was developing these things, and these are the semiconductor based on this 2D dimensional material, transition metal dichalcogenides. These are the potential applications and the field we can work on. And it is this 2D material is easy, and it has a low cost effect, and it is solution processable, so it is scalable, and the low temperature is easy. And the same 2D material as a thin film format people used to grow in CBD or like chemical vapor deposition or RTA, like based rapid thermal cooling techniques. So those are really using the vacuum and high energy consumption, and it has a long time, and the quality also matters, and the scalability is become problem. And the printable electronics is not at all possible with those techniques. So that's why the nanosheets electronics is attract more, because it can be used as a printable devices, because it can be formed as a ink type material, and it can be scalable. So here, there is some disadvantage. It is the film will not form for uniform film for large area. So that is the one disadvantage. And the interfacing between the nanosheets, between, if you have a 2-3 sheets, the interface between the sheets will be not that great. So my aim is to solve those things, and there is some disadvantage of defect, and I use that defect to attach some polymer onto that, and just the functionalization, like functionalizing that material with the defected part. So that is what I'm going to do in the next slides. And this is the general overview, how what are the methods are available to produce the nanosheets, 2D nanosheets. And there are some the available techniques only for, I'm talking about only for nanosheets. If thin film, then that is the different case, it is CVD and other process. And here I was thinking, I was using the exfoliation technique initially for my PhD work. I did this one actually. Like, you take a graphite big one, and with the scotch tape you peel it up, and you do the number of times, like 10 to 100 times, and then you transfer to your substrate. Then you will have your material. This is actually a graphene, and it will have this atomic this MOS2. Actually, MOS2 will have this kind of structure. And then the problem with this technique is, it is purity will be high, but the small size, we can fabricate only few device. We cannot fabricate large number of device in array at the same time. Like, it cannot be useful as a printable electron. It is only transfer to the solid substrate. And then the next approach is, the same graphite or some material with electrochemical intercalation, and then you can intercalate the um, uh, ions, some cations and anions inside the material with your applied bias voltage, and then you can uh, put this one into the sonication. Then they will have this, because of this ion intercalation, they used to when you put the sonication, and it will due to the applied energy, they can be separated and they can be deposited as a film. But here also the interfacing will have a problem, and for the long range. And the another problem is the low yield, and the quality is, it will have a single phase we will not get, because there will be some mixed phase will be there. And the next thing is solution phased ion intercalation. This is actually electrochemically, this is also solution based, and it is based on electrochemical. And here, based on the ion intercalation, direct ion intercalation. And if you take the bulk material and you put the some n-butyl lithium or potassium highly reactive material with particular environment condition, it will inserted inside the matrix of this 2D materials, and then you can put it into the sonication. Then you will get the phase changed material. Means here, if without any anion or cation, if you only put the solvent, and then if you put the if you use the sonication, it will come as a material with bulk nature. Bulk means the phase will be bulk phase, means 2H phase. mean 2H here. 2H is stands for semiconducting, and 1T stands for metallic. This metallic will have a metallic property, like the conductivity will be very high, and then their structure will have a little different. I was explained that one here. For example, you take this MOS2 and put lithium, n-butyl lithium, and then if you insert this material inside and then you sonicate, you will get the phase transferred material. Means how it is happening. For example, this is the crystal structure of the 2H phase MOS2. You can see that S and S, actually it is layer structure of molybdenum and sulfur, and top sulfur, middle molybdenum, and then down layer also sulfur. So this when in 2H phase, this sulfur and sulfur will be aligned in the same orientation. When you put it this lithium, and lithium gives the electron and tends to move this sulfur, rotate the sulfur in the clockwise direction for 60 degree, and it makes that makes the sulfur to move 60 degree away, and that makes this material the phase change. And due to this sulfur position change, makes this material metallic in nature. And the percentage of yield is achieved yield is around 73%. My case, it is around 71, like that. So it was like when you change this from here, this portion, it is semiconductor, there is a band gap will be there, 1.8 electron volt. When just after the intercalation method, your band gap will be nullified, and there will be zero band gap, and there will be no it is like behave like metal when you apply the voltage or current. So when you for this is the confirmation for that, when the 2H phase, the color will be light green, and because this transition of electrons, band gap transition, and when you make it 1T, then they become black color, and you will not have this transition, and the conductivity is drastically changes, and conductivity as well as the like hydrophilicity, it become hydrophilic. So means because of the phase change only, this hydrophilicity is happening. Conductivity goes to near to metallic, and this can also confirmed by the UV, because these A, B, C, D are absorption spectra, electronic and excitonic based absorption spectra, and 1T phase, you will have a only size dependent peak here, and it confirms that the material is phase converted. It is not 100% conversion, but it will be useful for some particular energy applications. Whatever we focus, it is enough to utilize this property. And when after confirming this one, when you now, my approach is to stretch this nanosheet. Okay, so I was initially just to take this in a solution and spray. I make the PDM. This is the stretchable electrode, stretchable gold electrode on the elastomer substrate, so it can stretch without any failure. So, but when I put that spraying this nanosheets or transfer the nanosheet over that electrode, and if I stretch it, they become this is the mechanism. Actual mechanism is this one. They actually slides, like sliding like this, and rotates at the same time, rotates, and when 20 to 30% strain, they can be go away from each other. There will be no physical contact. This electron flow will happen only between the physical contact, but when they slides and they go away, and there will be the distance between the sheets, so the electron flow will be cut down. And another problem with this directly using method is they used to poor addition with the substrate. and there will be a no polymer or nothing. So it is inorganic material. They don't have addition with this elastomer substrate directly, so they tend to move away, and the recovery will be very poor. Once you stretch it, then that's all, your device is gone. So this is not good for, and you can see the down images, and when I stretch it 20%, there is a crack, huge cracks is forming. So with this crack approach, it is not useful for the real application. So to avoid this crack formation, crack means the dislocation and movement of this sheets. To avoid this one, I was formulated some ink. um, this is the main idea of my work, and it is the first approach which is going to be reported very soon. And this is the phase changed 1T MOS2. You can see that there is some vacancy, means the defect. Some due to sonication and lithium intercalation, the sulfur will be removed from the atomic structure. So this case, when they when I do the sonication of breaking down this polymer like this, this is fluoroelastomer. We can take different type of polymer, but we have to find which one will be having the better interaction. Whatever the material you are preparing, it should be stable for like at least a week to the month. So if you are want to printing or any fabrication technique, should be, if your ink or the material is not stable, it is settling down, then it is not useful, because you cannot use a printable approach, or any industrial approach is not possible. So you are here I am formulating a ink means it can be, actually it is writable ink. I can write it whatever I want with particular 1 mm tip. I can write it. So because the size of these sheets will be in 200 nanometer, so along with blended with this material, I can easily write on any given substrate or paper or anything. So that is one approach. If you are formulating a ink, then your polymer you have to choose very carefully, because the polymer plays a huge role to stabilize as well as endure the strain when you stretch. So here I was using some of the fluoroelastomer polymers. This fluoroelastomer polymer, when I sonicated, they can be breakdown like this. This red color indicate that fluorine was there. Fluorine means it's the highly electronegative atom in the periodic table. So it can easily interact with some other electronegative material, as well as it will not bonding. It won't bond like covalent bond or ionic bond sharing, but it will interact electrostatically. It will interact. It pulls the material towards its side. And then the another one thing is the sonication is breaking down, as well as it's produced the some breaking down, that some of the fluorine rubber will come out of the surface of the polymer, and then that one will be intercalated inside. If you have if you have a notebook, you are just putting your hand inside the notebook in middle. You like so like that, the polymer goes inside your MOS2 fuel layer MOS2, and then it forms like stable ink. And then the attachment is really very less, but it will have an interaction. But intercalation, this fluorine, free radical fluorine can go inside. So they penetrated inside, and the fluorination can smooth the surface of the, means the friction between the sheet will be reduced because of the polymer and the fluorine intercalation. And that is why here atomically I was represented. And these are two layers, top and bottom layer. Then you have a polymer chain inside. It will penetrate inside. This one we can identify, because with the see, you can the interlayer distance. This is interlayer distance, means the layer distance between two nanosheets. And when you have a 1 TMOS2, it will be 0.76 or 0.75. When you, after formation, I checked it actually with the TM. This one was like around 1. I achieved up to 1.2, 1.3 3 nanometer. So it was huge high. Means the interlayer distance is increasing because of the fluorination and polymer intercalation. This one makes this material stable more than like 6 months, 7 months. Still I am using it. It was at the same time this kind of interaction is happening between fluorine and molybdenum, and they share just interaction between them, and it will be stable and it can be printable. Yeah. Yeah, these are the multiple application I can do immediately after developing the ink. It takes like just a 30 minutes job. Once your MOS2 and your polymer solution is ready, then you blend for 30 minutes. You will get a very good ink, and it can be spin coatable or anything. Like this is 4-inch paper. It means very huge substrate, and 4-inch paper you can make like thousands of devices over this. So we it can be like one time we can coat, and we without this polymer, this kind of coating, this kind of film formation is not at all possible. So the polymer choice is really important. And when I I use the flexible substrate, the addition is really good, and they are bendable also good, and it is doesn't change any property, is not at all changing with flexible. When I use the stretchable substrate, and then I coating over that, then I stretch even 100%. It was really stretching well, and when I release, it comes to its original position. Here you can see the ink drops with the printer. I drop this ink, and you can see that when I stretch, they are the shape of the ink drop is changing. This is actually quite thick. In this thicker one, it's showing this kind of reversibility also. Means reversibility means after releasing the strain, it goes to this original shape again. Means this much thickness, this thickness, 1 mm thickness drop. So it is like, even with this thickness, it is stretchable and it can be recoverable. Means it's real good for the stretchable application. So, and after this coating techniques, I also used these are made with the spin coating techniques. And when I developed the ink, so I wanted to print, and we have a nozzle printed over here. So I print this structure, line structure, and some other structure also. It is possible to print also possible, and the viscosity is 800 cp. So this can be used for the all kind of inkjet printer. So this is are the device after printing, before and with stretching. Even with 100% stretching, it was in the naked eye, I could not see any cracks formation. So then so this mechanically it was working. So I want to know how the electrical performance. So in order to check the electrical performance of this particular developed ink, I was the checked with the strain. So it was, you can see these are the inks when I use a different concentration of polymers, and to find out optimum, which one is optimum for my next device fabrication. So with that this graph, actually we find out that this 0.28% of polymer into 1% of material will be very good for this conductivity as well as for stretchability. That is the with this test, that is the one we found, and it can be work more than 1,000 cycles. So I'm actually further I'm working on to develop this to 10,000 cycle without much. In the flexible case, it's working. I like 10,000 cycle flexibility is working, but stretchability, it is 1,000 cycle, and it is goes like 1.5 order different was there in the electrical conductivity. So I want to improve this. So I was working on this, and here is the approach. And then after checking the electrical observation, I was checking the morphology, how it looks like under stretching. So these are the OM image, and we cannot find any because of the resolution, like magnification. We cannot see any cracks in this OM image. But when I use with FESM, with the 50%, there are some cracks like, and dislocation is forming. But when compared to the original, like this one, like this, without any polymer, it was huge crack is forming. When I use with this ink formulated, then the crack was very less even, and the recovery also much better than the one without polymer. So that's why this ink is possible to utilized for the stretchable device. So what is makes this ink stretchable? So I want to know the mechanism. So what I did is, I observed this electrical and morphological properties observation. Then I found, I want to know what is the mechanism. So then I was checking this one. This OM image is the after washing the polymer. I washed like almost 8 times, sonication and washing, sonication and washing. After washing, I drop some solution on the stretchable substrate. Then you can see this red mark and follow this white mark. When I stretch it to 50%, you can see there is one more layer of this one is newly existing, and this is means here also there is, you can see the area of difference, and it was means that the uh, sheet under the one was there, and the top one is sliding over and sliding and exposing the newer sheet to the top. So this is the one sliding mechanism actually people reported for the electrode application. So similar kind of things was working here. And there is and because of this polymer, this is the actually the same similar thing I was schematically represented here. And you can see that for example, there are 3 sheets, and they are intercalated with the polymer, and some of the polymer is in the basal plane also. And when you stretch it, the top these layers are distance, means in case of without polymer, it 50% it will be a big crack, they go really away. And but in this case, with the polymer is pulling that, it is not allowing the sheet to move away, because the applied strain was endured by this polymer also. So this at the same time, when I release it, it goes to the original position, because of the polymer is goes to the original position. And that's the cross sectional view here, it will be more clear to explain. And see, for example, two stack of sheets, and they are intercalated and interfaced with in between polymers. And when you stretch it, this interfaced polymer will be stretched more here. You can see I was thinned the one, and it was stretched, and then when you release it, it comes to the original position. And further, that fluorination also helps to reduce the friction force between the nano sheets. So that also helps the smooth sliding and things. And in case of this one, we couldn't observe any rotation. Actually, in case of normal electrode and other cases, the rotation of the nanosheet under stretching makes the huge cracks, and it is dislocates, where the cyclic stability will not be there because of the rotation of the material. Here, because the polymer is holding, it has a very good adhesive with the substrate as well as with this material. They are not allowing the sheets to rotate actually. So it is allows slightly to slide, not much, slightly slide, and it can come back, and pushing back when you release the help to go back to original when you release the strain. So that's why it is like useful for the this application. So I want to use this one for my stretchable applications, any application, because here up to this I found that this material is possible to utilize for some application. Until this only we studied the characterization part. So I want to utilize this stretchability of this material to some real device application. So we plan to, because this 1T-MOS2 is metallic phase and it has the electrochemical activity. So this electroactivity is because of the it comes because of this metallicity and hydrophilicity, as well as this oxidation state plus 2 to plus 6. So it has this ability, so we can utilize that one to make a real capacitor. So here we check the supercapacitor property by fabricating the device, and the capacitor performance is because these are very small micro supercapacitors. You can see this is the printed one, and the printed here we print actually over the, this is a stretchable substrate, and we print make the electrode first, then the top of that we print the active material, this 1,2-MOS2 ink, and then we stretch, and it has the even unto 40% strain. It is the relative capacity was retained. Even when you release, it goes to this is the recovery part. Here it goes to its original position. And here we demonstrated the LED operation, means when you stretch also 40% stretch, the LED intensity is not dropping down, means your device, your capacitor is working fine. Where this is actually coupled with the 3 capacitor here. 3 capacitor connected in serial, so it will just to add up the voltage of the device to turn on this LED. So that's why we are using this kind of approach to make. So it was successfully fabricated, and further my development on this one is the efficiency wise, it was little we are expected more, but it is little low. The means the compared to the published other stretchable electron supercapacitors. So we want to further improving this property by adding some intercalating some other atoms or CNT or graphene into the interlayer of the MOS2. That is my next plan. So this is actually the work summary is like we are developed some stretchable electroactive ink, which can be which produced by the intercalation of the fluorinated polymers, and the fluorination free radical fluorinated polymers will induce the stretchability as well as endure the strain and stabilize the ink. And the device fabricated with this one is the supercapacitor retains around 80% of capacity retention. So it will this approach, I just actually I was here, I just reported for only one. Actually I was developed quite 3, actually totally I was developed 3 electrodes, 3 material. It is like I used MOSC2 also and WSC2 also. The once you achieve this 1T phased material, this methodology is the generalized method, so you can utilize for all these kind of TMD materials. So it is possible. And then so it is the when we can utilize for other materials like other 2D materials also. I am thinking but we have to choose the polymer based on that material's property. So then we can develop this generalized technique to few more materials also possible. And it's a future perspective. You think about it, it's we need if we want to have a rollable mobile, like now we have a mobile with solid, and if it is fall down it will break down. So next we can just fold it or roll it and put it in the pocket and move away wherever you want. You can don't worry about the mobiles, and even it fall down, it will be like you can cruise it. Actually, you can roll it and you can whatever, you can play with it. It's a toy, like um, uh, how the children scratch the some papers or uh, papers or plastics, like that we can use our phone when we develop these electronic devices. Actually, I'm here only, I reported the stretchable energy storage property, but I was working, my real work is transistor and dielectrics. So I was doing all those things. I maybe if I have a next time, I can discuss about the transistor, only transistor, because one time everything will be it's difficult, it will be get confused. So I was strict with this technique. Maybe in future I can discuss if everyone is interested. And this as a conclusion, the flexible and stretchable electronic is the next big thing. It should be sure, even in the business wise, research wise, and it has a huge potential in all the field, like from the medical and aerospace, space technologies, and like day-to-day life events, like if you are doing exercise, you can monitor your body problems. So these are the things. And mobile phones, smart mobile phone will be stretchable smart mobile phones. So it will takes like long time. I think minimum it will takes at least 10 to 15 years. If the development of the stretchable electronics is rapid and it is developing well, but still there are so many obstacles was there. So internalization will take a huge time, and it is in the laboratory scale now. Some small devices are in commercial application, but still the major part, the basic building block of the stretchable electronics is stretchable transistor, that is in the under developing stage. So once it's developed, then this is the next big things. So that's all. Any questions? And
Thank you very much, sir, for that wonderful lecture. Everyone, the session is now open for questions.
Sir, one question that I have to ask is, what about the
yes,
power
sure.
supply, sir? Power supply, what about the, if it becomes stretchable electronics and what about the power source?
Yeah, this power source, actually we can use cell power charging devices. Actually, stretchable self power charging devices. Few of my even my colleagues were developing that one, and it is like when you stretch it, like your hand is moving. If you attach the supercapacitor as well as the energy generating material, for example PVDF, it is like nano generator, basically a nano generator. It will be attached with the supercapacitor. It also as stretchable. Under stretching, it can hold the energy. When you use that one, when it can be, when you stretch it or bend it, the piezoelectric tend to generate the voltage, and it will be transferred to the super capacitor that can hold, that can be applied to the stretchable. And now stretchable batteries and stretchable supercapacitors keep on developing. And so that is from the we can, if we build the structure, then we can plan and we can fabricate the stretchable, but from the power from we have to charge the battery or a supercapacitor from outside, so that become the problem. So people also developing the solar stretchable solar cells, so that can be mounted on the top of the device, stretchable device, as well as the stretchable nano generator. It will be like will be useful as a power source for the small scale devices. But if you want to use as a mobile phone and these things, the similar things, similar charging phenomena, but the batteries and supercapacitor will be stretchable.
Thank you, sir. Thank you. Students, who is responsible for the question answer session, ma'am? Vishwa?
Yes, ma'am. I'll do it, ma'am.
Okay, do.
Sir, there's two questions in
Yeah,
the chat box. I'd
sure,
like to read
sure.
it to you.
Yeah.
Pradima R is asking, will the techniques be a threat to privacy, data theft, and will these techniques be secure?
Sorry. Come again.
Will the techniques be a threat to privacy, data theft, and will these techniques be secure?
Here, for this one, what is the? I don't get the point actually. Uh, Here, what is the data?
சார் நீங்கள் ஃபர்ஸ்ட் வந்து லைக் இந்த ஸ்ட்ரெச்சபிள் எலக்ட்ரானிக்ஸ் மூலிமா நம்ம ஹார்ட்ல அந்த இது லைக் நம்ம ஹியூமன்
Yeah,
பாடியில்
yeah.
டெவலப்.
Okay. You are asking for there. Okay. Okay. The question is from introduction part. Here. So here that right now there is no such a things happen because it was not implemented inside the inside. It is in the practical level when it is comes to the personalized. I think we have to develop the better software techniques to handle those things always. Even with now the current technique, there are so many illegal things are happening. We have to keep develop our proxy to be safe. And this data transfer things will be you have to they will actually we have to create the software to keep it secure. And it I right now with this question I cannot answer this properly. I'm sorry actually. I didn't aware of this one, so maybe I will look into it. And maybe I will let if I'll give you my email ID, then I can put it.
Sir, there's one more question.
Yeah, sure.
Won't these stretchable electronics affect the biological systems of our body? Like it won't affect the blood vessels and nerves?
No. Actually, the thing is, the implantable devices are made with bio degradable or bio compatible material. So, with we can't use all the materials for the implantable application. So the people are really aware of that. They are already developing like that materials only. It is biocompatible or it can be biodegradable, so it won't affect those kind of things. And when use the external approach for like attachment, I have shown in the introduction, like attaching on the skin, that is it not necessary all the material should be biocompatible or biodegradable. But when you implant inside your body, then it should be biocompatible or bio degradable.
So good evening, sir. Myself, Arul Arasan. I'm one of the staff.
Okay, sir.
And I have a question. So you said like there are more than 50 nanosheets, 50 materials for the stretchable electronics. Which is the most commonly used material for this stretchable electronics, sir?
In 2D materials, there are actually graphene is widely used based on the approach. Actually, it is not intrinsically stretchable. The intrinsic stretchability of the graphene is only 5.3 to 5.6%. So it is not really intrinsically we cannot use for application. Like we need at least 10 to 15 the stretchability for at least small devices. So the graphene the people used with the buckling structure more. For the case of transistor they used, as well as for the energy device also, supercapacitors also they used, and CNT, particularly CNT. Actually that is one dimensional, but in two dimensional graphene used. And now people are working on MOS2 more.
Okay, if that is the case, then which is the best method to synthesize graphene nanosheet?
Graphene nanosheet, actually I will say the Umbus modified method, because that will give you your yield more. Because this kind of approach, you need a more yield with high conductivity. If you bottom up approach, if you synthesis, you start from bottom up approach, you will get material, but the conductivity will be problematic, as well as the quantity. But when you use, if you want to nanosheet, then the Humbers method, modified Humbers method will be good. In the thin film form, there are CVD now industrialized, and they are like growing in the copper foil. So it's very huge film can be possible.
So could you give some examples for nano generators? Some of the materials.
Nano generator is first material PVDF. You can use. Then PVDF. Another material we used, actually zinc oxide is the piece. Actually PVDF, you want only piezo or tribo?
Piezo materials.
Piezo is zinc oxide is the first material, and PVDF, and then some barium titanate, and with barium titanate with a different shape. If you make a different shape, they will give a better piece of properties, as there is a coefficient, piezo coefficient. For PVDF it is high, and there will be a phase in the PVDF. You should be careful when you have the phase problem, alpha, beta, gamma phase, and only particularly I think it is in the alpha phase it will give alpha or beta, I'm not sure, but it will give only in that particular phase will give more piezo potential energy. And in case of 2D material, if you are asking, MOS2 single layer will give, actually single layer, 3 layer, 5 layer, those things will give piezo potential, but it will not be great, but it can generate piezo potential.
Yes, sir. And in the SEM images, in the optical microscope, a crack is not seen, and in the SEM image, crack is observed. And if you use a polymer, crack is not observed. What is exactly happening, sir? Why the crack is not appearing?
Oh, in OM, it is not up. You are talking about here?
Yeah, yes, sir.
This one actually in OM, the resolution, see the scale bar is 500 micrometer, right? So yes, it's very, the crack is only like 1 micrometer, 2 micrometer. So you cannot, it's impossible to see through this magnification. So that's why in OM it is not visible. In SEM it is visible. We focused, and there is we can find without polymer. I told the mechanism is like the polymer is holding the material, and it is not allowing the material move freely. So it is restricting the movement as well as the rotation of that. And because of the interaction, some interaction between the fluorine, I was judging that because based on our study, based on the fluorine has electronegative interaction with this MO or sulfur, as well as the defected oxidized area. So that is restricting the movement of that one. So that's why it is giving less cracks.
Fine, sir. Thank you, sir. Thank you so much. And one last question, sir.
Yes, sure.
In India, like in generally, like we don't generally manufacture silica or semiconductors. We used to import it from other countries.
Yes.
Okay, so why is it happening like that? Why Indian scientists, we were not able to manufacture the semiconductors in a large scale?
Actually it is industrial questions, and it is involved in politics also. And it is actually the thing is one big thing. China is dominating in this field in silicon. They have a wide silicon source. Why China want to occupy Taiwan, and why they want to rule all that sea source? They want to. They are telling their part. No, that is actually it is silicon. And their case in the silicon was the sea source level, and then they're not there. They have a desert full of silicons. So they are very, and their industry was very good. and they are easily developing, and even Korea, some of the product is coming from China. And so in our part, we have to more I think it is come to from the politics, policies, and scientists. We have to be together, make a vision, and make to work in like this field and develop electronics devices, because without electronic devices we cannot live after this. So but every time we are buying, and we are importing, so the price is too high. And if it is, we can develop, and maybe it is possible. There are industrialization of this kind of
Yes,
device.
sir, I understand, sir. And the continuation of this, there is one more question. So I understand that the quality of silica in Indian soil is different when I compare it with Taiwan, China, or USA.
Yes.
Initially you said like the efficiency of silica has to be more when we start manufacturing or when we start research. We have to purchase a good quality silica material.
Yes.
So naturally, in India, the quality of silicon in which we are having it, which is less, the efficiency is less.
There is another, efficiency is less because the quality. If you make better quality, and the doping percentage perfect, then you will have if you want to P plus plus for particularly per transistor, or N plus plus per transistors. If it is really that carrier concentration, if the carrier concentration is quite good, then your device will work fine. If it is less, whatever your device is good, whatever the voltage you keep increasing and applying, then it will not be it's not easy to achieve their results. That is all comes from the quality of the material, and it is really important. And the mobility is, the carrier concentration is also plays a real role in the mobility of the device.
Sir, how many research groups are doing research under the stretchable electronics in India, sir?
In India, there are, I found few papers from the IIT Kharagpur, IIT Bombay, and some paper from JNCR. I think that has collaborated, but it's not many. And now my friends are joined in CSIR. They are just started.
Thank you, sir. Thank you, sir.
I don't know
That's it
much.
from my side.
I don't know much. Maybe it is. I know only these things. I don't know. Maybe if you know, you can share.
Thank you, sir. Thank you so much for answering all my questions.
Yeah. Thank you.
Sir.
Yeah.
Sir, when we were talking about the nanosheets, one of the major disadvantages was the scalability of the electronics. And also the main problem we face with the solar cells, right from the germanium, let be semiconductor solar cells to the Dyson stage solar cells, the efficiency is a major disadvantage in solar cells. When you talk about the the storage devices using nanosheets, sir, how does this scalable? It's not even that much scalable from nanosheets to the solar cells. How does it affect the efficiency, sir? Does it improve the efficiency when we use these nanosheets or thin films?
Actually, people with the nanosheets, there is no solar cell. There will be a disadvantage if you use solar nanosheets. Actually, it's need a thin film. Because thin film approach will be better for solar cell. If you are using there is this nanosheets, the interface and the percolation between the current flows through percolation. Okay, if the percolation is not good, then you will lose. But particularly in case of solar, you will get the energy if you don't want to waste that energy without converting into electricity. Okay, so if you are using the nanosheets, I think it is not a good idea, because the interfacing issue will come. If you want to use the 2D material, then use it as a film. For the stretchable solar cell, the people use the silicon actually. Silicon only they use, and graphene. So these are the things they grow in the film format, and they used. I didn't see any paper using the nanosheets for solar cell. Stretchable solar cell.
Yes, sir.
Yeah.
Sir, I have a question.
Okay.
You said that in future we'll be having rollable phones and like that, sir. How will
Yeah.
we ensure that there is no short circuit between the components in the motherboard, sir? We use now aluminum wires and all. If short
Yeah,
circuit happens,
actually we embed all those things on top of the elastomer substrate. It is actually an insulator, and then the circuits will be also packed with insulator material. Actually thermal conductive material. If any leakage happens, immediately the thermal conducting material will grasp that heat, and it will solve, as well as the actually they make insulation in each layer. They make even the current PCB is we can, if you check that current PCB, cut it in and check in TM, you will see like 7 layer, 12 layer, 15 layer, like that. They each layer will be insulated between one among that. So then that's why we can only problem current mobiles, some China mobiles we are facing is the battery. When the battery explodes, that is the one problem. But when we that's why people now are developing the non-lithium ion batteries for particularly for this stretchable electronics. If that non-lithium will be there, then it won't explode like lithium do. So it will be okay, possible.
sir, and also what materials are thought to be used as screens, sir, when we use those foldable ones? We are now using glass for our screens in the mobile phones.
Yes. Actually, we can use the PDMS. PDMS is transparent. There are so many. We can use PDMS is the transparent one, as well as polyurethane. Then PVEVA, polyethylene vinyl acetate, and there are so many substrates are possible. It is there are so many options are available. No problem. Only if the sensor can work under this encapsulation. There is strain sensor also developing, and there are so many sensors is coming up. So it is easy to utilize those things, particularly based on the ion gel based one. If you it will be encapsulated with this PDMS, and if you even touch, they can be sense, and it can work as your phone display.
Okay, sir. Thank you, sir.
Yeah.
So, are there any more questions?
Yarka, questions irka?
Hello, sir. I have a question.
Pragdish.
Hello, sir. My name is Pragdish, and my question is like, if these materials are stretchable, like to what percent they will like what could be their breaking point or fracture point? Like how long they can withstand?
Actually, you can. It's based upon the. There are some polymer concentration also plays a role. That some of the without polymer, it is up to 20%. They can slide through and it will go out. Based on the polymer concentration, it is keep increasing. With particularly the electrical, actually it can be stretchable like 100%, but the electrical percolation will be breakdown in around 45 to 50%, with in my case. But when goes to the other material, if you electrode, there is some material called liquid metal. It is can be stretchable up to 500%. So 500, if blend with polymer, they can be stretchable. Recently our group was published in Nature Material. They are like, it is like we can stretch more than 1000% as an electrode. But my focus is based on the active material. Active material means it can store energy, or in transistor it is a semiconductor. So it can modulate the electrons flow. So my focus is at this one. Only based on this nanosheet, I achieved in case of semiconducting, I achieved 50%, and in case of metallic phase, I achieved 50%. When I use the dielectric, I achieved more than 60 to 70%. So so it's based on the material and the polymer, how they interact, and how strong they are. The same polymer I use with graphene, it is not stretchable, because this polymer has graphene will, the disadvantage of graphene nanosheets, they have a lot of functional points, means functional groups. So they tightly bond, covalent bond with the polymer we add, so they become gel-like. So it will not be stretchable, not gel-like. It will be gel. When you stretch, when you dry it, it become brittle. So if you touch it, it will be breaking down. But in case of this particular TMD materials, I found quite interesting, and it was when I stretch, it was not that. When I mix with polymer, it is not blended. Or there are some other polymer I used. Those are not giving this kind of approach, means result. But in case of particular, you have to choose the polymer. You have to study, like, and I studied almost like 20-25 polymers. Then I found out this. So you have to study like that to find out which one will give you more, and how much stretchability, and then you have to find out more. If it is published one, then I can tell, but if you want to find, you have to do this R&D work.
Okay, thank you, sir. One last question.
Yeah.
How about these, usually the semiconductors, they are not much toxic, like only when you go like arsenic or like gallium arsenide, they tend to be toxic when you use it for 20 years, and when we are throwing it away, it becomes a problem, environmental issue. Similar to that, how about these materials, sir? Are they toxic? Do they pose environmental issues?
No, it is not toxic at all. It's even MOS2, they are MOS2 graphene, they are using biological application. So so it is not a problem. This is not a contaminating material. The contaminating material I use this worried about the lithium. It is if you are not properly washing or cleaning, and if you are throwing out, then it will be interacted with lithium ion. Actually, it is interacted with water or moisture, then it will be blast. That is the only material in this whole things. I felt it was quite dangerous for the environment. Remaining after this, once you washed with proper solvent, actually you have to neutralize that one with hexane. If you use hexane and those some organic solvent, they react with lithium, and they make lithium hydroxide, and then it will be nullified, and there is no problem with that. And we have to carefully discard that material to the waste, where we put that chemical waste separately. So that is the one thing. The other, this MOS2 or gold we use, or PDMS, these are not a problem for the environment.
Okay, sir. Thank you, sir. Thank you so much.
You're welcome.
Vishwa, any more questions?
So one more question, sir.
Yes.
So you said that within 4 and 5 years we will be having the mobile phones in our hand. That is a flexible mobile.
Yeah. Hope so.
Is that applicable for only mobile phones or other electronic device?
No, other electronic devices are already there. The wristband and many patches for the pressure sensing and things are already in market. And I think LG, Samsung, they are already in the competition. Who will going to LG proposed this one in 2013, and they are doing it, and they already succeeded. Foldable, like it will be fold like our laptop. So they will be very soon. They will launch. Maybe I'm expecting that.
Okay, sir. Sir, if you launch this mobile phones, then I want to know about the expensive of the solid and this mobile phone, sir.
Oh my God, I don't know that now currently. We can compare when it is comes to, and if you are enough luxury to buy it, then okay. Otherwise, we can have our own way of using it and buying it. And if it is actually flexible, if we really want, then if it is comes commercialized and it will be less cost, then we will go for it. Otherwise, they won't commercialize otherwise. If because people if not buying, then their business will be stopped. So they will think all those things before marketing that.
Okay, sir. Thank you, sir.
Are there any more questions? Fine. If there are no questions, thank you very much, sir, once again for spending valuable time with us, sir, and inspiring us with this topic.